Okay, we've done reciprocal trig ratios already. We know what they kind of represent. I guess I can write them down over here. We know that the reciprocal of sine is not the one that starts with that letter. So cosecant theta is 1 over sine. Secant theta is 1 over cos. And cotangent theta is 1 over tan. So if we remember chapter 5, reciprocal graphs, we should be able to graph the reciprocal trig ratios based on our knowledge of the regular ones. So just quickly to show you, if I wanted to graph sine x here, so this is y equals sine x or sine theta, it doesn't really matter. It's just whatever variable is next to it. I know sine starts at 0, 0, and it goes up to 1 after a quarter of the period. I've already scaled it in a quarter of a period. And then it goes back down to 0, and then it goes down to the minimum. I don't have dotted lines today, but it's okay. Okay, and this is one cycle of sine x. One cycle. Why'd I go to 3 pi? I don't know. Because I had the space, so why not graph 1.5 cycles, just because. Okay. If you want to do arrows on the end, of course you can. It goes on forever, unless you are restricted in its domain. And there I got sine x. Now, the reciprocal, as you would expect, y equals 1 over sine x, or cosecant x, is going to be like chapter 5. So every 0 of sine x is going to be a vertical asymptote. It's all going to be vertical asymptotes. An infinite amount of vertical asymptotes. Now I'm regretting going to 3 pi. Could have done less work. Okay, so these asymptotes are on the zeros. These, think of it as like individual parabolas, just like flip. So if this is at 1, the reciprocal of 1, you might think it's going to be plotted down here, but this is 1. So the reciprocal of 1 is actually 1. So these points are all the same. The reciprocal of -1 is -1. But all these points, as they get smaller and smaller and smaller and closer to 0, if they're in the denominator, they're going to go higher and higher and higher. So this is the graph of cosecant of x. Okay, in hindsight, I should have made this the 1 just so we can see more of the shape of the reciprocal function. And that's all there is to it. We know the intersection points occur at 1 and -1, so those are my intersection points. And then as this decreases, the reciprocal increases. Let's do cos. The only difference between sine and cos is cos starts at the maximum. Cos starts at the maximum. This is y equals cos x. Starts at the maximum every quarter of the period, goes to the middle, goes to the minimum, goes to the middle, max, middle, minimum. That's a terrible minimum, but who cares? And plot cos. Arrows. And now I want to plot the reciprocal. So exact same way, this is going to be secant x. So I look at my zeros. They're a little shifted from sine because sine and cos are shifted by a quarter of the period. So I draw my asymptotes here at the 0. My intersection points are still these guys. These are still points on both functions. And then I can look over here. Well, this is going down. That means the reciprocal must be going up to the asymptote. This one is going up, must be going down over here. This one's coming down. Sorry. Decreasing, and now it's increasing. So even I tripped out over there because I'm drawing it decreasing, but from left to right, it's increasing. Over here, same thing. So it actually looks exactly the same as this, which of course it does. Sine and cos look exactly the same. They're just shifted from one another. Okay, so it's not much different. The only thing you mainly have to know is that 0 becomes that asymptote. So very, very important. Okay, just one more thing over here. Cotangent, because it equals 1 over tan, I'm not going to graph cotangent, but because it equals 1 over tan, and tan is sine over cos, the better way to think of cotangent is cos over sine. Okay, that's the better way of thinking of cotangent. And the reason for that is there's only 2 things that we really need. is when the numerator is 0, when the denominator is 0. When the numerator is 0, I have an x-intercept. When the denominator is 0, I have an asymptote. So every time sine is 0, which I should know that by now, I'm going to have an asymptote. Every time cos is 0, I'm going to have an x-intercept. And those x-intercepts, eventually in chapter 7, those become solutions to problems, because we always solve for x-intercepts. So it's really important to really know that numerator, especially when it's 0. And that's it. 6.5 is super easy.